The next topic that we're covering in Unit 1 is the squeeze theorem. And the squeeze theorem states that if you have three functions, function g, function f, function h, the letters don't matter, and if g is less than or equal to f and f is less than or equal to h, then when the limit of g of x and h of x both equal L, or any number, when they're the same, then the limit of f is the same. What does that mean? This part up here means you have three functions. G is always going to be less than f. F is always going to be less than h. You have three lines. They could look crazy, bonkers, whatever. But h is always going to be on top. F is always going to be in the middle. And g is always going to be in the bottom. If they give you this criteria and it's true, then if g and h ever have the same limit, then f is going to have the same limit too. So for example, if these two lines came up and like touched up here, and they had the same limit right here at this point, that means f would also have to have this limit because it has to be in between them, or at least equal to them here. So that's what this means. Now we're going to apply this to a graph to kind of like make it make sense, give a concrete example. So if you have this graph right here, you have x squared cosine 1 over x squared, right? And you're trying to find limit when x is approaching 0 on this graph. How would you go about that? You like, yeah, I don't know how to plug 0 into this. It's crazy bananas cuckoo, right? So what do? Well, it's a cosine graph, and you know cosine graphs go like this. They're wavy, and they top out at 1, and the lowest point is -1, right? That's all you need to see is that it's a cosine graph. You don't need to see the specifics. So you know that this function here, cosine 1 over x squared, is greater than -1 or equal to, and then less than or equal to 1, right? Because it's a cosine graph. Okay, so once you establish this inequality and you know that it's in between -1 and 1, you need to apply this x squared right here that we've kind of just been ignoring. It's there, but we got to put it in. So how do you turn this into this? You multiply by x squared, and anything that you do to one side of an inequality, you have to do to both sides. So if you multiply this by x squared, cos 1 over x squared, you have to multiply this and this both by x squared, and you keep the inequality here. I'm gonna write this up here to make it like, you know, more pretty, more like not cluttered. Cos 1 over x squared is less than or equal to x squared. So now you have this. So you're trying to find the limit, so then you'll plug in limit of 0 to each. So you could write it out. Most people will skip this step, I'm not gonna lie, but since it's the first time ever seeing this crazy, amazing concept, we're gonna write the whole thing out. Squared less than or equal to limit, oh, this is negative, I'm sorry, x approaching 0 of x squared, right? And then we use substitution here. We plug 0 into each. You have 0 is less than or equal to, this limit stays the same because we're not plugging that in, that's too much. It's x squared. X squared cos 1 over x squared less than or equal to 0. So if you have 0 on both sides, and this has to be equal or less than or greater than both of these, that means that the center is also going to be 0. So we could see that the limit of this equation here is 0. And what's cool about this is if you look on the graph, this is the original equation. This is x squared cosine 1 over x squared. And we take the left equation, negative x squared, and it's always going to be greater than this. And you take the right equation, x squared, and it's always going to be less than this. And you see it makes this shape, and when they meet in the middle at 0, they're all touching. And since it has to be in between the two, it gets squeezed, and you can see that right there, it equals 0, and all three equals 0. So that's the basics of the squeeze theorem. You really do not use it that much, but I think it's cool, and I think that this graph in particular looks really cool. All right, moving on.